Welcome to our second lectures on device physics and the fourth lectures of advanced power electronics and control. We shall continue with our discussion which we have left in our previous discussions, that was thyristor. So, we have told that actually we have commercialized this product is commercialized in 1960 and it has replaced thermionic based emissions switches like vacuum tubes and all, and it is used for the high power handling capabilities, and true power electronics starts with the inventions and application of the thyristors. So, what essentially thyristor is? Thyristor is essentially we can think of that one PN junction diode, another PN junction diode is connected in series. So, essentially what happened, since when you applied a voltage, actually let us say VA is greater than VK or cathode, then these junctions, this J2 is automatically going to be reverse biased, and this junction J1 and J3 is forward biased, and that gives a features of forward blocking capability. So, this device is normally off. Why? If you apply a voltage VA greater than VK, junction J2 is reverse biased, only leakage current will flow. Similarly, if VK is greater than VA, then naturally J3 and J1 are reverse biased, and then also it will be blocked. But you can make it on with the external devices or external way. So, for this reason, you got to get, you can inject external current that will basically break down the junctional barrier of J2, and it comes into the forward conduction mode. Please mind it, never give a great trigger while Vk is greater than Va, it may damage the thyristor. So, let us come into the discussions. The thyristor is a 4 layer, you have a 4 layer P, you can name it P1 N1, P2 N2 like that. 3 terminal devices, you got anode, you got cathode and you got gate, which each layer consisting of alternatively PN type material. For example, PN, the main terminals are labeled as anode and cathode across the full 4 layers, and the control terminal is called gate, and it is attached to the P type terminal near to the cathode. So, this is the configuration of it. And what happen if you actually truncate the thyristors, then you can see a 2 transistors. So, it is said to be a 2 transistors model PNP and NPN, and in between they have got a connections. So, generally thyristor is analyzed by the 2 transistors model for its turn on applications. So, different kind of thyristors appearance, this is the symbol of the thyristors, this is anode, cathode and gate, and you will have a different kind of pictures. That is basically the heat sink, it required to put onto the heat sink. This is anode, and ultimately it will be go into the heat sink, and we can tighten the screws, and there is a different kind of segments, and current handling capabilities of the thyristors in fax devices, it can go as high as kiloampere rating. So, power handling capabilities of these devices can go as high as megawatt level. So, this is the actually a truncated version of the thyristors, So, we can visualize as two transistors model, one is PNP, another is NPN, where actually Ig is injected. Thus, if you write the KCL from this point to this point, ultimately Ia becomes alpha Ig plus ICB1, this is basically the base current of transistor 1, and ICB2 is the base current of transistor 2, and you will find that 1 minus alpha 1 plus alpha 2. Here this alpha 1 and alpha 2 are essentially are not constant, this value can change depending on the value of injections of this value, and generally this value is alpha 2 generally changes, and it may so happen that by changing this value, this denominator can be made close to 0, and thus high current will flow, and we say that thyristor is triggered or latched, and it will continue to flow till some external action is been added to actually put it off, or commutation. Commutation itself is a big chapter of discussions, but with the invention of the GTOs and all those things, there is a literally phasing out. So, let us come to the different layers and its concentrations. So, it is called P emitter region, this is called N base region, there again it is called P base region, and it is N emitter region. So, this is the model, and a highly resistive region N base region is present in all thyristor to give a blocking capability, and it is the region, the N base and associated junction J2, which must support the large applied forward voltage that occurs when switch is off, or the forward blocking state, or the non-conducting state. So, this is the region. High voltage thyristors generally made by diffusing aluminum or gallium into both the surface to create p-dope region, forming a deep junction in the N base. So, that will reduce the on state conduction loss. The higher forward blocking voltage of the thyristor, the thicker N base region, it is basically used. However, increasing the thickness of this resistive region will actually reduce the operations, reduce the faster operation, that means it will slower the turn on and the turn off. So, it will take larger time to turn it on and require higher gate current, and also you have to do the commutation, put it off when actually you may have a natural commutation when in case of the rectifier operation, when you apply it to the AC sources, you get a negative voltage applied cathode to anode. So, thus turn off also will be slower, and it will be suitable for the low frequency switching devices, because most of the trap charge required to be removed, and that takes lot of time than the faster devices. So, there are something we require to trade it off, we have to put according to the applications. So, if the thyristors has a high blocking forward voltage, generally it is a slower device, and switching time will be actually slow. Between forward blocking voltage rating and the forward voltage drop during conduction should be kept in mind. Since high voltage thyristors generally of the aluminum and the gallium drop surface, so that gives a higher voltage blocking capability, but it also increases the on state conduction losses or the resistance of the devices. So, we have to trade it off. So, for this reason we require to choose a suitable devices. We should not choose a high blocking thyristors where we will find very high conduction losses, and reverse, you choose a devices which has a low conduction losses, but it cannot sustain that forward blocking capability or the reverse blocking capability, then circuit will burn simply. So, for this reason designer has to judicially use these features of the thyristor. operation. When anode is positive potential, that when VAK is positive with respect to the cathode and no voltage is applied to the gate, it is said to be the forward blocking mode. The junction J1 and J3 are the forward biased, while junction J2 are reverse biased, and J2 will actually block the whole voltage. If VAK is increased beyond the breakdown voltage of VO that has been prescribed in the data sheets for the thyristors, avalanche breakdown of J2 takes place and thyristors start conducting, but sometime it may damage the thyristors, because when actually it start conducting, current is also high and it has got a considerable voltage drop across this junction, and that if you properly heat is not dissipated, this mode may damage the thyristor. If applied a potential Vg at the gate terminal with respect to the cathode, the breakdown of junctional voltage J2 occurs at considerably lower voltage. It can be as less than 10 times less or 20 times less, depending on the amount of the current you are injecting. By selecting the appropriate value of the Vg, the thyristor can be switched on a certain state. So, this is the IV characteristics of the thyristors. Once Vg is 0, so this zone is called the forward blocking region and the current leakage current will flow through it, and thereafter what happens, forward leakage current will flow through it, and thereafter when it will cross to the value of VBO, it will be triggered and current will flow from this. If you keep this value of Ig of some value, let us say here around half of the VBO, so or 2/3 of the VBO, it can actually come this point to this point and it will give you a drop, a very small drop. Similarly, you can turn it on from the video. Again, you please remember that Ig2 should be much greater than Ig1. So, larger the gate current, you get lower the forward blocking voltage. So, apart from the gate triggering, there are different method of the triggering. Avalanche breakdown, that is actually high voltage applied across the anode and cathode. DVD triggering, if you apply a high rate of change of voltage, that also leads to the triggering. For this reason, it is not advisable to use thyristors in pulse kind of waveform. If you have a square pulses which has a very high DVDT, which may falsely trigger the thyristors. So, for this reason we will not use it most of the cases. And light activation thyristor, that is a special kind of thyristors when a depletion region can be actually reduced by activation of the light or doping charges and high junction voltage, and what we generally use is that gate triggering. Gate triggering is something we use for the triggering thyristor, that is a common mode of practice. A different kind of gate triggering can be there, that is RC, or we can have a UJT based gate triggering, that different kind of gate triggering circuit may be used. So, characteristics of the thyristors, let us come to it. So, blocking occurs when reverse bias current is supplied depending on the gate current. When forward biased and the gate current is applied, conduction takes place and it will be high current and ultimately it will be blocked by the load of the system. Once turn on goes on, gate is no longer required. You can put off the gate, so it will just require to turn it on. Once it is turned on, gate circuit may be put off, and thus you can avoid a constant dissipation of the current across the gate. Gate turn off when decreasing current goes to 0 because of the external power circuit also. Now, this is actually the switching characteristics of the thyristors. So, this is actually the voltage across VAK, that is anode to cathode voltage, and it will drop. You can find that current through the thyristor will take around 10% time to actually to its peak value, it would, whatever time it will take, 0 to 10% or the leakage current you can assume to be 0 to 10% of the load current or the final rated current. So, that current is said to be TD or the delay time. Thereafter, you will have 10 to 90%, we say that it is a rise time. So, faster is the rise time, so faster, that will be a faster device. If rise time is slower, it will be slower device. There it takes some amount of time to actually settle down, and TGT is the get turn on time. Similarly, we come to the reverse recovery time. Reverse recovery time totally depends on the current. Reverse recovery time is the total current actually TRR, and this one is actually TGR, and total time is said to be the turn off time, that is represented by the TQ. Again, actually in like that we require, it is a very important features of the reverse recovery time. So, for this reason, when it will be off? When both are recovered. The recovery time means actually it has got a forward blocking capability, but if you have a false triggering, again it will turn conduction. For this reason, we got a forward recovery time, or this total actually combines, and then we can say that thyristor has hold the forward blocking capability. So, you have to wait till time TRR plus TGR. So, there are few important terms, that is forward breakdown voltage VBO, that is it has been prescribed by your data sheet. It is done by the destructive test of the devices. Generally it does not survive after the test. So, we generally will do with the few samples and presented in the data. So, this is VBO, and that is called forward breakdown voltage, and once it was actually in a forward mode, forward blocking mode, some amount of current will flow, that is called forward leakage current, that is around 10 to the power 4 times lower than this actually the thyristor current, and thereafter you have a gate triggered. So, accordingly voltage will change, and this is a forward conduction drop. Generally this length is almost at, due to this ohmic losses it will be little bit slanted. So, if it is, because as there are two diode in series, this model is essentially, can we think of that two diode put into the series, and since the silicon based diode, of course you can assume that both will have a junctional drop of J1 and J3 in forward conduction mode of 0.7 and 0.7, that gives to the 1.4 volt. But depletion reason is made in such a way by dropping of the aluminum and other things, but forward conduction mode we try to restrict less than 1.4 volt. That is actually one of the technical advancement has been achieved in case of the thyristor. There are two important parameter. One is called latching current. Latching current is associated with the turn on process. Once thyristor is put on, thyristor current required to go more than the value of IL. Then if you remove the gate, then also it will be in a forward conducting mode. So, thus the minimum anode current is required to maintain the thyristor on state immediately after its turn on and gate signal has been removed. Same way holding current. What is holding current? This current should, minimum current it should hold to keep it in a conduction mode. So, that is called the holding current, and that is associated with the turn on of the thyristor. If the current is above the holding current, thyristors will stay in a forward conduction mode. The minimum anode current maintain the thyristor in a on state, and of course, from this figure it is quite clear that this holding current should be less than the latching current. Now, these are the few parameters, it is quite important while analysis the thyristors and use it the thyristors. First of all, peak working forward blocking voltage or forward offset voltage, VDM. So, this is basically the VDM, which is quite important because it is a repetitive supply if you there. So, this voltage has to be block. You may trigger this point, you may trigger this point, you may trigger this point, you may trigger this point. So, safely it should be able to block the value of the VDM, that value will be prescribed. So, peak repetitive forward blocking voltage, this is VRM, because sometime we may have a notch and notch actually follows. So, that value will be actually peak repetitive forward blocking voltage. Peak non-repetitive or the surge blocking voltage, if all of a sudden high voltage comes, that is said to be the surge and it has not has a periodic occurrence, then that voltage is said to be the actually VDSM, and the VDSM value also will be prescribed. Some notches may come maybe after 1 hour or 2 hours or even after a day. So, that value actually said to be the VDSM. Peak working reverse voltage, it is same. So, as this actually forward voltage, this is basically VRWM, this one. There at a peak repetitive reverse voltage, this one it is same as this one, but it is in a reverse direction. Peak non-repetitive surge, so this will be this one and this has to be actually almost reciprocal to the forward voltage. And we require to understand that forward DVD rating. So, this is quite important. You know that supply voltage undergoes some changes. If it is say sinusoidal wave, it is quite slow. If it is a pulse kind of voltages, then it will be have a very fast DVDT. So, DVDT rating of this device required to be prescribed. Otherwise, we require to put a DVDT protection circuits, that is called snubber. We shall take out the circuit protections in totality. Thereafter, voltage safety factors, that is VSF, that is given by peak repetitive reverse voltage by 2 into RMS value of the voltage. So, some value will come out, accordingly life of the device will be decided. So, more the safety factor, more will be the life of the device, but definitely cost of the component will go high. And finger voltage of SCR, that is called FV. So, these are the few parameters has been prescribed in your data sheets and we will continue to actually have a operating on those data sheet for the practical design aspects. Apart from that, we have current ratings, that is same, that is maximum RMS current rating, and thereafter maximum average current rating, mostly it will be for the DC value. Maximum surge current rating, all of a sudden if high current comes, it has to sustain, and Thyristors I square R rating, so for the conduction losses, mostly when it is on state, and thereafter DIDT rating. So, it is if it is undergoes very high DIDT, then also it can damage the thyristors. For this we require to put a DIDT protecting circuit, and that we will discuss about the DIDT and DVDT protections, but thyristor has to ensure that we will have its DIDT rating, we are operating in a safe region. Thereafter, we have some specification on the gate current. So, gate current to trigger, there will be a minimum current, there is a safe zone operation where it will not trigger, because noise also gives you some amount of the gate current, but that should not trigger the thyristor falsely. So, for this reason gate current to trigger, that value will be there. Similarly, we will have some value will be there, actually we shall come into the discussions. So, gate voltage to trigger, there will be some voltage. So, this Vg and this Ig, this is the minimum value. This zone will not trigger, this may come due to the noise. So, non-triggering gate voltage, this is basically non-triggering gate voltage, and peak reverse gate voltage, the maximum voltage you should apply, you should not go beyond that it may damage the gate. Peak reverse gate voltage, again that comes into the picture in a reverse mode. So, you should not allow actually the reverse gate voltage. Average gate power dissipation, this is the power line. So, you have to fix it within the power line. You should not go beyond the power dissipation, otherwise the gate circuit will fail. And peak forward gate current, that value also will be specified by the thyristors. So, this is the data sheets of the thyristor. You see that there are some values. It has a forward blocking capability of 1200 volt, and it can carry as high we are discussing a diode of 3 ampere or 8 ampere, and it has a power handling capability of the 50 ampere. But you see this ratio, this gate current is 1000 times less. So, this is the efficiency counts, the IGT is actually 50 milliampere, and all the values is provided what has been discussed into the data sheets. So, in a different temperature level, in a conduction temperature 50 amperes, if it is temperature rises to 100 degree centigrade, it has to be considerably derated, it has to be operated to the 31 ampere, and all the data has been prescribed. So, peak gate current can be 8 ampere, peak power dissipation should be 1 watt, and maximum peak reverse voltage is 5 volt. Similarly, you will see that actually what should be the IGT. IGT should be it actually prescribed that is 50 milliampere, but you can operate anywhere in between actually 8 to 50, so that you can turn it on at different voltages. Similarly, holding current has been prescribed when gate is open, that is 500 milliampere. Similarly, latching current has been prescribed, that should be actually 1.2 times of the IGT. So, from there you can calculate, and this value is generally it is actually 1 to 5 milliampere. So, these are the, and value of this DBDT also is given, that is actually 1000 volt per microsecond. Similarly, value of the TQ, that is the turn off time, you can see that is in the range of the 100 microsecond. Please recall that it is quite slow. In diode we have come out, we have seen a fast diode having a turn off time in nanoseconds, and a snappy diode will have around 2 or 1.2 microsecond, but this will take a considerable high amount of time to turn it off. So, turning it off of these devices, it is quite slower because of the trap charges in junction J2. Okay, we shall continue to our discussions. These are the ratings you can follow. So, these are the threshold voltages and IDRM and RDRM. So, all those data has been actually explained, so that student can take out for the design purpose and how to read the data sheet properly. We shall continue to tell few aspects of the thyristors in our next classes, and followed by some modern devices like IGBT and IGCT. Thank you so much for your attention.